Right. So what is actually at the edge of the universe? And if we built some wildly overpowered spaceship, pointed it in one direction, and just kept going, what would we eventually run into? This is one of those questions that sounds like it should have a very simple answer, and then cosmology immediately comes along and ruins your afternoon. Because first we have to ask, what do we mean by the universe? Do we mean all of space and time, full stop? Do we mean the part of space that can ever send us information? Or do we mean the part we can see right now, because light has had enough time to reach us since the Big Bang? And those are not the same thing. Not even close. So let's do this properly. We're going to separate three different edges. First, the edge of the observable universe, which is the limit of what we can currently see. Second, the cosmic event horizon, which is the limit of what we could ever reach or communicate with in the future. And finally, the truly enormous question, whether the entire universe itself has an edge at all. Let's start with the number you have probably heard before. The observable universe is about 93 billion light-years across, or about 46 billion light-years in radius. That number is already a little sneaky, because it does not mean the oldest light we see has been traveling for 46 billion years. The universe is only about 13.8 billion years old. What it means is that the stuff that emitted the oldest light we can see, the cosmic microwave background, is now about 46 billion light-years away from us because space has expanded while that light was traveling. That boundary is called the particle horizon. It is the current distance to the most distant matter that could, in principle, have had any causal connection with us. In other words, it marks the edge of our known universe, not the edge of everything, just the edge of what has had time to say hello. Now, here is where the trap is. You might think, fine, let's just fly there. But cosmology is not a normal road trip. That 46 billion light-year distance is a proper distance. An instantaneous distance you would measure if you could somehow freeze the expansion of the universe, lay out an absurdly long cosmic tape measure, and ask, how far away is that region right now? But the universe does not freeze for us. Light does not travel through a static stage. It travels through space-time, and space-time is expanding. So the path that matters is not just a distance through space, it is a path through space-time. Even if you had a spaceship moving at the speed of light, you would not reach the particle horizon. As you traveled, the space between you and that horizon would keep expanding. The finish line would not just be far away, it would keep receding in exactly the wrong way. So, practically speaking, the particle horizon is not a destination, it is a viewing limit. And now for the slightly sad bit. The universe also has an event horizon. We usually meet event horizons around black holes, cross the boundary, and light from inside can never get back out to the outside universe. But expanding universes can have horizons too. There are galaxies whose light we can see today, because they emitted that light long ago. But if those galaxies sent us a brand new message right now, that message would never reach us. Space between us and them would expand too quickly. Based on our current cosmological measurements, the cosmic event horizon is roughly 16 billion light-years away. That is much closer than the particle horizon. So there are galaxies we can observe right now that we could never visit, never phone, never send a postcard to. We are seeing their past light, but they are already outside the region of the universe we can ever interact with. Honestly, that is both beautiful and a bit heartbreaking. The universe is not just big. Parts of it are slipping permanently out of causal contact with us. Over time, more and more distant galaxies will pass beyond that horizon. Their old light will fade and redshift away, and the reachable universe will become lonelier. Unless, of course, we cheat. So let's cheat at least as a thought experiment. Einstein's speed limit applies to objects moving through space. Nothing with mass can locally move faster than light. But space itself is allowed to expand in a way that makes distant regions recede from each other faster than light. That loophole is why people talk about warp drives, Alcubierre bubbles, and all sorts of gloriously ridiculous engineering that would require energy budgets we do not have and probably should not be trusted with anyway. But imagine we had one. Imagine a spectacularly irresponsible warp ship powered by the energy of entire stars. We blast through the cosmic event horizon. We chase down the particle horizon. We arrive at the place that used to be the edge of everything we could see. What do we find? Almost certainly, more universe. And this is the important point. The particle horizon is not a wall. It is not a glass dome. It is not a cosmic border fence with a little sign saying, "End of universe, please turn around." It is the limit of our view from here. If you moved somewhere else, your observable universe would move with you. You would look back and see the matter that eventually became the Milky Way as a tiny hot patch in your own cosmic microwave background. Around you, you would probably see more galaxies, clusters, voids, filaments, and all the large-scale sponge-like structure we see from here. So, if there is no wall at the edge of the observable universe, where could a real edge be? That depends on the geometry of the whole universe. On the largest scales we can measure, the universe looks very, very flat. Not flat like a sheet of paper in the everyday sense, but flat in the geometric sense. Parallel lines stay parallel, triangles add up the way you expect, and the cosmic microwave background and galaxy surveys do not show strong evidence for large-scale curvature. But very flat is not the same as perfectly flat. This is where we have to be careful. If the universe is exactly flat, then the simplest version of general relativity says it may be infinite. You keep going forever. More galaxies, more voids, more cosmic web, possibly infinitely much of it. And infinity is not just very big. Infinity is a whole strange beast of its own, with uncomfortable implications, including the possibility of repeated regions if the universe is infinite and matter arrangements are finite in number. But do we know the universe is perfectly flat? No. We know it is flat to within the precision of our measurements. Think of standing in a field on Earth. The ground looks flat because you are tiny compared with the planet. But go high enough, and the curvature becomes obvious. The universe could be the same kind of trick, just on a scale so enormous that the observable universe is only a tiny patch of it. If the universe has a small positive curvature, then space could be finite but unbounded, like the surface of a sphere, except with one extra dimension in the analogy. A two-dimensional creature walking on the surface of Earth can travel forever without hitting an edge, but if it goes straight long enough, it comes back to where it started. Our three-dimensional space could, in principle, be the three-dimensional surface of a higher-dimensional hypersphere. In that case, our absurd warp ship might eventually loop all the way around the cosmos and return home. But do not pack snacks yet. Estimates suggest that, even in the most optimistic allowed case, the radius of curvature would be so enormous that you would need to travel at least many times farther than the distance to the particle horizon, something like 18 particle horizon distances at a bare minimum under simplified assumptions. And that is before remembering that the universe does not kindly pause its expansion for your sightseeing trip. There is another possibility too. General relativity is extremely successful, but it is not a complete theory of everything. Ideas connected to cosmic inflation suggest our observable universe might be part of a much larger inflating structure, perhaps one bubble among many in a larger multiverse. A bubble universe could have something like a true edge, depending on the model. But then the question becomes even stranger. What is outside the bubble? Are the laws of physics the same? Are there the same dimensions? Does outside even mean what we think it means? That is not a place where we can just confidently announce an answer. That is a place where we say, here is what our observations tell us, here is what our models allow, and here is the bit where the universe has not given us enough data yet. Frustrating? Yes. But also, this is exactly where science gets interesting. So, final answer. The observable universe has an edge, the particle horizon, about 46 billion light-years away in proper distance. The reachable universe has a smaller edge, the cosmic event horizon, roughly 16 billion light-years away, but the entire universe may have no edge at all. It may be infinite, it may be finite and curved back on itself, or, in more speculative inflationary models, It may be one region inside something much larger. What happens if we try to get to the edge? With ordinary physics, we cannot. With imaginary warp physics, we probably just find more universe. And if there is a deeper edge beyond that, it is not just a travel problem. It is a what is space actually problem, which is, frankly, a much better question. Now, quick question round. First, is it circular to use general relativity to test predictions about the universe when those predictions also depend on general relativity? Not really, but the concern is sensible. A theory becomes powerful when it makes many independent predictions that all survive testing. General relativity predicts planetary orbits, gravitational lensing by the sun, the behavior of binary pulsars, the bending of light by galaxy clusters, and gravitational waves. It is not accepted because it explains one thing beautifully. It is accepted because it keeps explaining different things with the same underlying rules. Second, if dark matter is clumpy, why are stars and planets not full of it? The key is that dark matter does not seem to interact electromagnetically. Normal gas can lose energy by radiating light, cool down, collapse, and form stars. Dark matter mainly interacts through gravity, so it can gather into huge halos, but it cannot efficiently dump energy and collapse into dense star-sized objects in the same way. It stays much more puffed up. And finally, can we please stop throwing hypothetical monkeys into black holes? Yes, absolutely. No monkeys are required for this cosmology lesson. The universe is quite dramatic enough without us adding that.